Two pebbles. We have a pebble being thrown straight up, and it has an initial velocity of 16 meters per second from a height of 1.4 meters above the ground. At the same time, a second pebble is dropped from a height of 14 meters above the ground. Find the time when the two pebbles reach the same level above the ground, then find their velocity, and then find their landing velocity after they complete their little trajectory and land back on the ground, and find the landing time difference of the two pebbles. Find the time when the two pebbles reach the same level above the ground. So what are we looking here? We're looking for a position, and we're also looking for a time. That leads us to the second kinematics equation. So we're going to solve it for each pebble and then put a requirement on it. They have to land at the same point right here. So we'll call that point Y, where Y up, that's the pebble that we're throwing up, and Y down is the pebble that's just being dropped. We will get two equations, a system of equations, and then we'll solve them, and we'll take up as positive. So here's our general equation here, the second kinematics. Here's the equation for throwing the pebble up in the air. We have an initial position of 1.4, an initial velocity of 16, and then we have acceleration from gravity, which is going to be half at squared, this term right here. So that's a negative 4.9 t squared. The pebble that we're dropping down has an initial height of 14, no initial velocity, and again, here's the acceleration term. We set those terms equal to each other because we want them to meet at the same place. And look what goes out right here. Acceleration term cancels because it's the same for both pebbles. Once the pebble leaves your hand, if you're throwing it up, or once it leaves wherever you're dropping it from, they're both subject to the same acceleration, so that just cancels out. We're left with a term in t, and also this 12.6, and we solve it and find out that at 0.79 seconds, these pebbles reach the same point. Find the velocity of each pebble at this point. Well, what did we find on the previous slide? We found time, which was 0.79 seconds, and we want to find a velocity. So that just leads us to the first kinematics equation. And then the acceleration, of course, is negative g. We just substitute in our values for time. And here's our up equation. You have an initial velocity. The down pebble has zero initial velocity. So at the point where they meet, the up pebble is doing 8.3 meters per second. It's still going up. And the pebble going down is a negative 7.7, which makes sense. I mean, that was falling from the second it was dropped. So those are the two velocities. Compare the landing velocities of the two pebbles. Well, since we know the displacement of each pebble, and we're trying to find velocity, we'll use a third kinematics equation. So we'll take the first one here. This is for the pebble thrown up. And you can see we have v squared up equals the initial velocity squared minus 2g delta y. Delta y is our displacement. And the displacement, your final position is 0, and your initial is 1.4. So we put the numbers in, and we come up with negative 17 meters per second, which is good because we know it's heading in the down direction. And why did we take the negative root, right? When you take the square root, it can be plus or minus. Well, you have to apply the physical condition to the math, and we know it's heading down when it falls, so we use a negative root. For the pebble that just falls, we have no initial velocity, and we just have this term, and we find out that that is also minus 17 meters per second. Now, don't read too much into that, okay? That's just true to two significant figures. If you were to take some more sig figs, you'd find out that the numbers are different. So correlation here is not causation. There's no relationship between those two velocities being so similar, other than that's how we chose the initial conditions. Find the landing time difference of the two pebbles. We're going to use the first kinematics equation, and we'll have the landing velocities calculated in part C for the pebbles. So here's our equation, and the acceleration is negative g, and let's start with the pebble falling down. The final velocity, the landing velocity, is equal to the initial velocity in the down direction minus gt. We rearrange the equation to solve for the landing time, and then we substitute in our values. Here's the negative 17 we found before. The initial velocity was 0, and we come up with 1.7 seconds for the pebble that is falling before it hits the ground. We then move to the pebble that we threw up. It had an initial velocity in the up direction, and again, here's your minus GT factor. We rearrange for time. We put in our initial velocity of 16, our final of negative 17, and we get 3.4 seconds, which makes sense because when they met, all right, when they met at this point here, it's not a terribly good arrow. Let's try again. There's an arrow. And the other pebble was coming down here. This pebble still had an upward velocity, so it had to go up like this before it came down. This pebble sort of had a head start, so it hit first. So the numbers seem to check out. And to complete part D, we just have to subtract the 2 times. So the difference in landing will be the one going up, which takes longer, minus the one coming down, and we get delta t is 1.7 seconds.